Question 2C. The letters A, E, I, O, and U are vowels. Part 1. How many arrangements of the letters in the word algebraic are possible? Firstly, the word algebraic contains 9 letters, and I've written it here on this dash diagram. We're interested in the number of ways that these 9 letters can be arranged among themselves. So we're dealing with an ordered arrangement or a permutation. Now, another point to note is that the 2 letter A's obviously repeat. So we need to take that into account later on when we're determining the total number of arrangements. So firstly, the number of ways that 9 letters can be arranged among themselves, assuming that they're all different, is 9 factorial. But we need to divide by the number of ways that the repeating letters can be arranged among themselves. So I've added subscripts here just to tell these letter A's apart. So these A's can be swapped among themselves and it doesn't make any difference to the arrangement. And that can occur 2 factorial ways. So the total number of arrangements is equal to 9 factorial divided by 2 factorial, which is 181,440 arrangements. Part 2. How many arrangements of the letters in the word algebraic are possible if the vowels must occupy the 2nd, 3rd, 5th, and 8th positions? Just like part 1, we're dealing with an ordered arrangement or a permutation, not a combination. Now the word algebraic contains 4 vowels, of which one of them repeat, the letter A. And I've called them A1, A2, E, and I. Now there is a restriction, and the restriction here is that the 4 vowels need to be placed in positions 2, 3, 5, and 8. So we'll need to work out the number of ways that these 4 vowels can be arranged in these 4 positions, taking into account this repetition of the letter A. Then we'll work out the number of ways we can arrange the 5 letters around these 4 vowels. And then finally we'll apply the fundamental counting principle to work out the total number of arrangements possible. So the number of ways these 4 vowels can be arranged is 4 factorial divided by 2 factorial, since the 2 factorial represents the number of ways that these letter A's can be arranged among themselves. Arranging the remaining 5 letters can be done 5 factorial ways. And then applying the fundamental counting principle by multiplying 4 factorial over 2 factorial by 5 factorial to give us the total number of arrangements. And that's 1,440 ways. Question 3A. 7 people are to be seated at a round table. Part 1. How many seating arrangements are possible? This is an ordered circular arrangement. The idea here is that we pick one person at random and then seat them randomly around the circle. And that person acts as a reference point. Then we arrange the remaining 6 people around the first person. Here is a circular dash diagram that may represent the situation. So I've just picked a random person, say person 1, seated them somewhere around the circle, it doesn't matter where, and then we arrange the remaining 6 people around person number 1. And this can be done 6 factorial ways or 720 ways. Part 2. 2 people, Kevin and Jill, refuse to sit next to each other. How many seating arrangements are then possible? This is an ordered circular arrangement with a restriction, and the restriction here is that Kevin and Jill cannot sit next to each other. There's 2 ways we can go about this. We can use complements, where we determine the number of arrangements where Kevin and Jill are sitting next to each other, and then subtract that from the answer in part 1. Or we can seat Kevin first somewhere around the circle, determine where Jill can sit such that she is not next to Kevin, so count the number of ways that that can happen. Then we arrange the remaining 5 people around Kevin and Jill, and then apply the fundamental counting principle, multiplying these 2 values together to get the total number of arrangements possible, where Jill and Kevin are not sitting next to each other. So here's a circular dash diagram that may represent the situation. So I've seated Kevin somewhere around the circle, so here's Kevin. And I've put 2 X's here where Jill cannot sit. So that leaves 4 remaining positions that Jill can choose such that she is not next to Kevin. And that gives us 4 ways that that can happen. Now, arranging the remaining 5 people occurs 5 factorial ways. So by the fundamental counting principle, we multiply those 2 values together and we get 480 ways that Jill and Kevin can be seated such that they are not next to each other. Question 3A. How many 9-letter arrangements can be made using the letters of the word isosceles? Let's write down the word isosceles and take note of the letters that repeat. So we have one I, one O, one C, one L. We have 3 S's and we have 2 E's. Now this is an ordered linear arrangement with repetition, and that needs to be taken into account when working out the total number of arrangements. Now assuming all 9 letters are distinct, they're different, then there's going to be 9 factorial ways of arranging those 9 letters. But we have 3 S's, so 3 letters that repeat, and we also have 2 letters that repeat. So we need to divide by the number of ways that the 3 S's can be arranged among themselves, and also the 2 E's, the number of ways that they can be arranged among themselves. So the total number of arrangements is equal to 9 factorial, so that's arranging the 9 letters, and dividing by 3 factorial, 2 factorial, which is the number of ways that the S's can be arranged among themselves, and the number of ways the 2 E's can be arranged among themselves. And that equals 30,240 ways. Question 2E. A 4-person team is to be chosen at random from 9 women and 7 men. Part 1. In how many ways can this team be chosen? Firstly, this is an unordered linear arrangement, so combinations will be applied, not permutations, to determine the number of teams possible. We have 16 people, from which 4 will be drawn to make up a team. So the number of teams possible is given by 16 choose 4, which is equal to 16 factorial over 12 factorial 4 factorial, which equals 1,820 teams. Part 2. What is the probability that the team will consist of 4 women? The number of teams consisting of 4 women is given by 9 choose 4, which is 9 factorial over 5 factorial 4 factorial, which equals 126. So out of the 1,820 teams, 126 teams will consist of 4 women. So the probability that a team consists of 4 women is given by 126 over 1,820, and that simplifies to 9 over 130. Question 3C. Sophie has 5 coloured blocks, 1 red, 1 blue, 1 green, 1 yellow and 1 white. She stacks 2, 3, 4 or 5 blocks on top of one another to form a vertical tower. Part 1. How many different towers are there that she could form that are 3 blocks high? Firstly, this is an ordered linear arrangement. The blocks are of different colour, and we're interested in the number of ways that Sophie can stack the 3 blocks where the order of the colour is important. Now this is a permutation, not a combination. And we can use the fundamental counting principle to determine the number of ways that Sophie can stack 3 blocks. Now the first dash represents the first block, and Sophie has 5 colours to choose from. The second dash represents the second block, and she has 4 colours to choose from since Sophie's already chosen 1 colour here. And then the third dash represents the third block, and Sophie has 3 colours to choose from for that space there. So 5 times 4 times 3 is equal to 60. Part 2. How many different towers can she form in total? We'll consider 4 cases. Case 1. The number of ways Sophie can stack 2 blocks is equal to 5 times 4. So a dash diagram here showing 2 blocks. Sophie has a choice of 5 colours for the first block and a choice of 4 colours for the second block, and that gives us 20 ways. Case 2, 3 blocks, and that was worked out in part 1. 5 times 4 times 3, there's 60 ways that Sophie can stack 3 blocks. Case 3, 4 blocks, that's 5 times 4 times 3 times 2, 120 ways. And case 4, 5 blocks, that's 5 times 4 times 3 times 2 times 1, and that equals 120 ways. So the total number of arrangements is 20 plus 60 plus 120 plus 120 is equal to 320 ways that Sophie can stack 2 blocks, 3 blocks, 4 blocks, or 5 blocks. Question 5b. Mr. and Mrs. Roberts and their 4 children go to the theatre. They are randomly allocated 6 adjacent seats in a single row. What is the probability that the 4 children are allocated seats next to each other? This is an ordered linear arrangement with restrictions, so permutations will be applied. Next, we'll have a look at the number of ways the 6 family members can be arranged in a row without taking into account the restriction. And this occurs 6 factorial ways or 720 ways. Now we'll consider the restriction. So the number of ways the 6 family members can be arranged where the children sit together may be modeled using a dash diagram. So here are the 4 children grouped together, so that'll act as one entity, and then we have the 2 adults, so Mr. and Mrs. Roberts, so those will be the remaining 2 entities. So the number of ways these 3 entities can be arranged is 3 factorial, but then we multiply by the number of ways that the children may be arranged within their group, and that's 4 factorial. So the total number of arrangements, taking into account the restriction, is 3 factorial multiplied by 4 factorial, which equals 144 ways. So the probability that the 4 children sit together is equal to 144 divided by the total number of ways that the 6 family members can be arranged, which is 720, and that simplifies to 1/5. Question 4b. Barbara and John and 6 other people go through a doorway one at a time. Part 1. In how many ways can the 8 people go through the doorway if John goes through the doorway after Barbara with no one in between? This is an ordered linear arrangement with restrictions, so permutations will be applied. Let's consider the restriction. The restriction here is that Barbara has to go through the door right before John, so with no one in between. So I'll group John and Barbara together, and they act as a single group. Then I'll arrange the remaining 6 people around John and Barbara. And John and Barbara have to be in this order, since Barbara has to go through the door first. So there's 1, 2, 3, 4, 5, 6, 7 entities. And that can be grouped or arranged 7 factorial ways or 5,040 ways. Part 2. Find the number of ways in which the 8 people can go through the doorway if John goes through the doorway after Barbara. Here is a dash diagram that may model the situation. We have the door, we have 8 dashes representing the 8 people, and among those 8 people are John and Barbara. Now, without taking into account the restriction, that gives us 8 factorial possible arrangements or possible ways that these 8 people can enter the door. But we're only interested in the number of ways that this can occur where Barbara enters the door before John. And that can include any number of people in between Barbara and John. So Barbara and John can take any 2 of these 8 positions. And the 8 factorial includes the positions where John is before Barbara or Barbara is before John. So wherever the J and the B occur on the dash diagram, they can be swapped around. But we're only interested in the situation where Barbara enters the door first. So half the arrangements will have Barbara before John and the other half will have John before Barbara. So the total number of arrangements where Barbara enters the door before John is 8 factorial divided by 2 factorial ways or 20,160 ways. Question 3a. At the front of a building there are 5 garage doors. 2 of the doors are to be painted red, 1 is to be painted green, 1 blue and 1 orange. Part 1. How many possible arrangements are there for the colours on the doors? This is an ordered linear arrangement with repetition, so permutations will be applied. Here is a dash diagram that may represent the situation. So the 5 garage doors are represented by the 5 dashes, and we have 2 garage doors that are red, so that's the repetition. So we have red 1, red 2, green, blue, and orange. Now the total number of arrangements is equal to 5 factorial, which is the number of ways that these 5 garage doors can be arranged among themselves, divided by 2 factorial, which takes into account the repetition of the 2 red doors. And that equals 5 factorial over 2 factorial, or 60 ways that these garage doors may be arranged. Part 2. How many possible arrangements are there for the colours on the doors if the 2 red doors are next to each other? Here is another dash diagram that may represent the situation. The difference between this one and the one in part 1 is that the 2 red doors are grouped together, since we're interested in the number of arrangements of these garage doors where the 2 red doors are next to each other. So we'll group R1 and R2 together, so they act as a single group, And then we have the green, blue, and orange doors that are arranged around the 2 red doors that are grouped together. So we have 1, 2, 3, 4 items that need to be arranged. So the total number of arrangements is equal to 4 factorial, or 24 ways. Question 2e. Alex's playlist consists of 40 different songs that can be arranged in any order. Part 1, how many arrangements are there for 40 songs? And part 2, Alex decides that she wants to play her 3 favorite songs first in any order. How many arrangements of the 40 songs are now possible? Part 1. Our first consideration is whether order matters. And in this case, order certainly does matter. Now, Alex is going to order 40 songs. So for the first place, or the first choice, Alex has 40 songs to pick from. Once she's chosen a song, for the second choice, she has 39 songs left to pick from. For the third choice, she has 38 songs left to pick from. For the fourth choice, she has 37 songs to pick from, and so on. So by the fundamental counting principle, the total number of arrangements is 40 times 39 times 38 times 37 times 36, all the way to times by 1, and that gives us 40 factorial arrangements. Now for part 2, I'm going to split the dash diagram into sort of 2 parts. The first 3 dashes represent Alex's favorite songs. So she's got 3 favorite songs that she'd like to order in a particular way. So for the first 3 dashes, she has a choice of 3 favorite songs. Once one has been chosen, she has a choice of 2. Then once that has been chosen, she's only got 1 left to pick from. So there's 3 factorial ways of arranging her favorites as first, second, third place. And then that leaves 37 songs to order for the remaining 37 places. So the total number of arrangements in this case is 3 factorial multiplied by 37 factorial. Question 5. How many arrangements of the letters of the word OLYMPIC are possible if the C and the L are to be together in any order? We can use a dash diagram to help visualize the total number of arrangements. Now there are 7 dashes representing the 7 letters, and the letters C and L have to stay together. So I've written C and L and I've grouped them together using brackets. Now that means there are 1, 2, 3, 4, 5, 6 items that can be arranged in any order. So there's 6 factorial ways of arranging these 6 items. The C and the L behave as if it was 1 item. But within this set of brackets, the C and the L can change places, and there are 2 factorial ways of that occurring. So the total number of arrangements is 6 factorial multiplied by 2 factorial, which is 2 times 6 factorial, which is option D. Question 11e. In how many ways can a committee of 3 men and 4 women be selected from a group of 8 men and 10 women? Here is a dash diagram to help visualize the situation. There are 7 dashes representing the 7 committee members. Now, the first 4 dashes are taken up by 4 women, and the last 3 dashes are taken up by 3 men. Now we're going to choose 4 women from 10, where the order does not matter. So this is a combination. Likewise, we're going to choose 3 men from 8, again where order does not matter. So by the fundamental counting principle, the number of arrangements is 10 choose 4 multiplied by 8 choose 3, which is 11,760 combinations. Question 7. A family of 8 is seated randomly around a circular table. What is the probability that the 2 youngest members of the family sit together? Let P1 and P2 represent the 2 youngest members of the family. To work out the probability that P1 and P2 are seated together around this circular table, we need to work out the total number of arrangements where P1 and P2 are seated together and then divide that by the total number of arrangements. Now this is a circular arrangement, and that's represented by this circular dash diagram, and P1 and P2 need to stay together. Now because this is a circular arrangement, we need to fix one of the two youngest members first. So let's fix P1 around this table first. So I'm going to place P1 here. That leaves 2 factorial choices for P2. Since P1 and P2 need to stay together, P2 can either be here or here. That leaves 6 remaining places for the 6 remaining family members, and that can occur 6 factorial ways. Now the total number of arrangements after we fix one person in the circle, there's 7 other places left, is 7 factorial. So the probability that P1 and P2 are seated together, or the 2 youngest members of the family are seated together, is given by 2 factorial multiplied by 6 factorial over 7 factorial, which is the total number of arrangements, which means the answer is option A. Question 8. In how many ways can 6 people from a group of 15 people be chosen and then arranged in a circle? Our first step is to determine the number of ways that we can choose 6 people from 15 people where order does not matter. For that, we'll use a combination. 15 choose 6 is equal to 15 factorial over 6 factorial multiplied by 9 factorial, and that comes from the formula n choose r is equal to n factorial over r factorial multiplied by n minus r factorial. Now that we've chosen the 6 people, we need to arrange them in a circle, and we need to work out the number of ways that that can be done. We fix one person, and then we work out the number of ways that the remaining 5 people can be arranged in a circle around that person. And that gives us 5 factorial ways of arranging those 6 people in a circle. So by the fundamental counting principle, the total arrangements is equal to 15 factorial over 6 factorial multiplied by 9 factorial multiplied by 5 factorial. And this equals 15 factorial over 9 factorial multiplied by 5 factorial over 6 factorial. And incidentally, 5 factorial over 6 factorial is equal to 1 over 6. 5 factorial is just 1 times 2 times 3 times 4 times 5. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. There will be some cancellation, which I did not show here, but the end result is that 5 factorial over 6 factorial is equal to 1 over 6, which leads us to the result that the total number of arrangements is equal to 15 factorial over 9 factorial multiplied by 6, which is option D. Question 4. A rowing team consists of 8 rowers and a coxswain. The rowers are selected from 12 students in Year 10. The coxswain is selected from 4 students in Year 9. In how many ways could the team be selected? Firstly, the order is irrelevant. It doesn't matter in which order the 8 rowers are chosen from the 12 Year 10 students, or the 1 coxswain from the 4 Year 9 students. So we're dealing with combinations, not permutations. Now the number of ways of choosing 8 rowers from 12 is given by 12 choose 8. And the number of ways of choosing 1 coxswain from the 4 Year 9 students is 4 choose 1. By the fundamental counting principle, the total number of arrangements is 12 choose 8 multiplied by 4 choose 1. Therefore, answer is option C. Question 8. A team of 11 students is to be formed from a group of 18 students. Among the 18 students are 3 students who are left-handed. What is the number of possible teams containing at least 1 student who is left-handed? Firstly, this is an unordered arrangement, so combinations will be used, not permutations. Next, we'll consider the use of complements to determine the number of teams containing at least 1 left-hand student. And the complement of at least 1 left-hand student is no left-hand students. So the number of teams containing at least 1 left-hand student equals the total number of arrangements minus the number of arrangements containing no left-hand students. Now the total number of arrangements is 18 choose 11, and the number of arrangements containing no left-hand students is 15 choose 11. Since there are 18 students on the team, 3 of which are left-handed, 15 are right-handed. And that equals 30,459 teams, therefore option B. Question 10. 3 squares are chosen at random from a 3x3 grid below, and a cross is placed in each chosen square. What is the probability that all 3 crosses lie in the same row, column, or diagonal? Firstly, this is an unordered arrangement, so we'll be using combinations, not permutations. There are 9 choose 3 ways of selecting 3 squares from 9, and that equals 9 factorial over 6 factorial 3 factorial, which gives us 84 possible ways of choosing 3 squares from the 9. Now, of those 84 ways, there are 3 rows, 3 columns, and 2 diagonals that are possible, which gives us 8 ways out of the 84 to align the squares in rows, columns, or diagonals. So the probability of squares aligning in a row, a column, or a diagonal is equal to 8 out of 84, which simplifies to 2 out of 21, and therefore it's option B. Question 8. 6 men and 6 women are to be seated at a round table. In how many different ways can they be seated if men and women alternate? Firstly, this is a circular ordered arrangement with restrictions. That means we'll be using permutations, not combinations. Let the 6 women be W1 all the way through to W6, and the 6 men be M1 all the way through to M6. Next, we're going to choose a woman or a man and seat them at the table first. And this is because it's a circular arrangement. The first place or the first position, it does not matter since they're all considered identical. Then we're going to arrange the 11 others, taking into account the restriction around the first person we choose to sit at the table. Here is a dash diagram that may represent this situation. Woman number 1 is chosen first and is seated at the table. The remaining 5 women are then arranged around women number 1 in 5 positions. Now the 6 men need to be arranged in such a way that the women and the men alternate, and there are 6 positions that the men can be seated in. Now the number of ways that the women can be arranged in the 5 position is 5 factorial ways, and the number of ways that the 6 men can be arranged in the 6 alternating positions occur in 6 factorial ways. And by the fundamental counting principle, the total number of arrangements is 5 factorial multiplied by 6 factorial. Therefore, the answer is option B. Question 8. In how many ways can all the letters of the word parallel be placed in a line with the 3 L's together? Firstly, this is an ordered linear arrangement with restrictions and repetitions. That means the use of permutations, not combinations, to work out the total number of arrangements. Next, we'll deal with the restriction. The 3 L's are to be grouped together and will behave as one item. Next, we'll deal with the repetition. In the word parallel, there are 2 A's, and that will need to be taken into account when working out the total number of arrangements. Here is a dash diagram that may represent this situation. Firstly, I'll group the 3 L's together. And notice that I've put grouping symbols around the 3 L's. So this will behave as one item. Next, I'll write the 2 A's, and I've given them subscripts, so A1 and A2. And that can be swapped around, but it's still the same arrangement. So that will need to be taken into account. Lastly, the 3 remaining letters that don't repeat, P, R, and E, I've written in last. Now, the total number of arrangements is given by 6 factorial. Since there are 6 items to arrange, the 3 L's act as one item. 2, 3, 4, 5, 6. So that's where the 6 factorial comes from. But then we need to divide by the number of ways the A's can be arranged among themselves, since they repeat. Hence why the total number of arrangements is 6 factorial divided by 2 factorial. Therefore, the answer is option A. Question 8. Out of 10 contestants, 6 are to be selected for the final round of a competition. 4 of those 6 will be placed first, second, third, and fourth. In how many ways can this process be carried out? We may describe this situation as a 2-stage arrangement. Stage 1 involves an unordered arrangement where 6 people are chosen from 10, and stage 2 involves an ordered arrangement where out of the 6 people chosen, we're going to choose 4 people and then rank them first, second, third, and fourth. Now the number of arrangements for stage 1 is equal to 10 choose 6. I'm going to use combinations since order does not matter. And the number of arrangements for stage 2 is equal to 6p4 using permutations since order is important. Now by the fundamental counting principle, the total number of arrangements is equal to 10 choose 6 multiplied by 6p4. And using factorial notation, 10 choose 6 is 10 factorial over 4 factorial 6 factorial multiplied by 6 factorial over 2 factorial, which represents 6p4. Now the 6 factorial in the numerator here will cancel with the 6 factorial in the denominator here, and we end up with 10 factorial over 4 factorial 2 factorial. Therefore, option C is the answer. Question 12C. To complete a course, a student must choose and pass exactly 3 topics. There are 8 topics from which to choose. Last year, 400 students completed the course. Explain, using the pigeonhole principle, why at least 8 students passed exactly the same 3 topics. Firstly, we'll consider the number of ways a student can choose 3 topics from the 8. Now this is an unordered selection, so we'll use combinations to determine this. 8 choose 3 is equal to 56 combinations. So there are 56 different ways a student can choose 3 topics from the 8. Next, we'll consider the 400 students who passed a course, and a course consists of 3 topics. Now, the 400 students divided evenly over the 56 different combinations is equal to 7 and 1 over 7 students per unique combination. But the number of students who chose a particular combination must be an integer. This value here doesn't make sense since we're talking about a whole number of students. Now 7 and 1 over 7 is greater than 7. Hence, by the pigeonhole principle, at least 8 students must have passed the same combination of 3 topics. Question 10. The members of a club voted for a new president. There were 15 candidates for the position of president and 3,543 members voted. Each member voted for one candidate only. One candidate received more votes than anyone else and so became the new president. What is the smallest number of votes the new president could have received? The solution to this problem is based on the pigeonhole principle. Now each candidate on average received 3,543 divided by 15 votes, which equals 236.2 votes per candidate. But the number of votes cast is an integer, not a decimal. And one candidate was the winner and got voted president, which means that that candidate would have received more than 236 votes. So I would like to find out how many more votes that candidate would have received, at least as a minimum, to have been voted the president. Now something else to be mindful of as well, that one candidate received the most votes, not at least one, which means there was a clear winner. Now 3,543 minus 15 multiplied by 236 votes means that there were 3 votes remaining that need to be allocated to some candidates. So if we just assume that each candidate received 236 votes, not 0.2, but just 236 as an integer, multiply that by 15, subtract that from 3,543, which means that there's 3 votes floating around that need to be allocated somewhere. Now, by the pigeonhole principle, one candidate would get 2 out of those 3 extra votes, or those 3 votes remaining. So if we take 236 as the integer and then add the 2 extra votes that that candidate would have received, the minimum that candidate would have received to be the winner would equal 238. So therefore, the answer is option C. Question 11D. A committee containing 5 men and 3 women is to be formed from a group of 10 men and 8 women. In how many different ways can the committee be formed? This is an unordered linear arrangement, so combinations will be used, not permutations. We'll also apply the fundamental counting principle to determine the total number of committees that may be formed. There are 10 choose 5 ways of choosing 5 men from a group of 10, and there are 8 choose 3 ways of choosing 3 women from a group of 8. So applying the fundamental counting principle here, if we take 10 choose 3, multiply it by 8 choose 3, we get the total number of committees that may be formed. So that's 10 factorial over 5 factorial 5 factorial multiplied by 8 factorial over 5 factorial 3 factorial, and that equals 14,112 committees.